welcome back physics students. Today we are going to learn about how to combine electric forces. Electric force is just like any other force. It's considered a vector quantity, so it can be represented with a magnitude and it can have a direction. So we can add electric forces together just like we've done in any other chapter where we've added our forces basically from head to tail and stuff like that. So this section should be pretty easy because we already know how to add vectors. We already know how to add forces together. We just have to think of it as being an electric force. So actually I got to fix the iPad. Just give me 1 second. All right. So if we look at this diagram, you guys know how to add vectors together, so this isn't new to you. So just kind of a refresher here. Let's say we have charge Q3 here, charge Q2 here, charge Q1 here, and let's say we wanted to find the net force acting on Q1. Well, all three are positive charges, so it's going to create a repulsion force. So there's going to be a charge or a force here and a force here. So the force acting on Q1 by this guy here. There's a force acting on Q1 from Q2 here. So you have two forces acting on Q1. So you have this force and this force. So it's just like adding vectors. You just add them head to tail. So if I take this, move it over here, so which is in this diagram here, you can see that the resultant vector would be F1. So figuring out the force vectors, this isn't anything new to you guys. We've learned about this a long time ago. So like it says here, the electric force is combined by vector addition to give the total force. This addition process is referred to as the superposition of the forces. So it's just a fancy way of saying what's the resultant vector. So right here, F1 would be the superposition of all the forces. So let's look at a problem. Like it says, pretty easy stuff for us. It says a charge Q1 equals negative 5.4 microcoulombs. We should convert that to coulombs. So I'm going to move the decimal point over 6 spots. So 0.0000 0.054 coulombs. That's negative. So right here it'd be negative 0.0000045 coulombs is Q1. The charge Q2 is negative 2.2 microcoulombs. So I'll make that coulombs as well. So 1, 2, 3, 4, 5. And then we got 2, 2. Okay, and that's coulombs. And then it says at the axis point of 1 meter. So at this point right here, so this is 0, call that the origin. Q2 is located at 1 meter. Find the total force acting on Q3 when the Q3 is going to be 0.0000016. That'll be coulombs. When it's located at 0.75. So here's what you have to recognize is, let me make that negative, make this positive. You have to draw kind of the free body diagram acting on Q3. So you have to realize that there's going to be a attractive force between Q3 and Q2, right? So F of 3 on 2, so that'd be right here. You're going to see that there's an attractive force from Q1 acting on 3. So there's two forces acting on that guy right there. So then you just apply Newton's second law, and you can see that it's going to be this force subtracted this force will give us our net force. So down here, To find the force acting on that point, you have to take the force of 3 on 2 and you have to subtract the force of 3 on 1. So there's kind of our formula that we're going to need to use. So that's just like summing up our forces in the x direction. You guys remember that, right? Newton's second law. Summing up the forces in the x direction equals m times ax, or just summing up the forces in general. In this case, we have two forces acting on it in the x direction, so then the net force is this. So what force is acting on it? It's going to be the electrostatic force. So that's what we have to do here. We have to calculate the electrostatic force of this guy and then subtract it from the electrostatic force from that one right there. So that's just going to be, I'll plug in the numbers here. So that's just going to be our K times our Q3, our 2, Q3, all over the distance. Now, the distance between this guy and this guy will be 0.25 squared. And I'm just putting in Q2 and Q3 into here because I don't want to have to write this and that. So it's just a lot easier to call it Q2 and Q3. Just same thing with K, I'm just calling it K. When I plug it into my calculator, I'll use those values. But it is 0.25 away. Then I would subtract that from this force right here. So then I would go K, and then I would go Q1, Q3, over, now the distance from here to here is 0.75 squared. And to save some time, what I could do is I could use my fancy, remember that I was telling you guys Coulomb's law is going to be used quite a bit in this chapter. So program that into your calculator. Well, that's what I'm going to do because I programmed it in. So I just have to enter in these three values and it'll give me my answer. So when I enter in those values, we're going to get a 0.14 minus a 0.51. Let's see here. Or, I'm sorry. Yeah, it'd be 0.54. Well, let's see. I have that backwards. I'm sorry. Yeah, I'm sorry. Scratch that. It's going to be 0.51 minus the 0.14, which gives us 0.37 newtons. And that's going to be going in the positive x direction. So, yep, adding these vectors aren't really hard at all to do. So I'll let you guys work on that one. Let's try this one together as a group. It says, given that Q equals 12 microcoulombs and the distance equals 16 centimeters, find the direction and magnitude of the total electrostatic force exerted on the point charge Q1 in the following figure. All right. So we're given information. We're given that Q is 12 microcoulombs, and we're given that the distance is going to be 16 centimeters. So that's what distance equals. So I'm gonna move that, call that a meter, because that's what we need. I'm gonna take the microcoulombs, I'm gonna turn that to a coulomb, because that's what we need as well. So 0.0000012 coulombs, because that one's just Q. Notice how in here it says positive Q, so that would be 0.00012. The next one says -2 times Q, so that one's going to be -0.00000, and then times 2 would be 24. And then the last one is 3Q, so that's 0.00000, and then 36 coulombs. And that's actually going to be a plus. and this one will be a plus as well. So actually on our diagram we could say plus, negative, and plus. Because that's also important too, is you have to know the charge on your particle. So in this case, this one's the negative, this is a positive charge particle, this is a positive charge particle. And we want to find the total electrostatic force exerted on the point charge Q1. So we're looking for this one. So if I draw a free body diagram for Q1, and then I consider all the forces acting on it, I'll be able to calculate this. Well, between this force and here, it's going to be attractive. So there's going to be a force arrow going this way. So I'll draw that on the free body diagram. There's going to be a force on 1 by 2 going that direction, okay? Then over here, you can see that this is a plus and a plus. That's going to be a repulsion force. So there's going to be a force going this way, and that's going to be 1 on 3. So it's very important to draw the free body diagram, and that way you can see what's going on here. So you can see that when we sum up our forces, we do our forces in the x direction here. It'll be F12 subtract F13. That'll give us our net force. So force will be F12 minus F13. And then we just plug in the information for it. So, and it's the force in this case is calculated with that Coulomb's law. So that'll be K times Q1, I'm just going to call it, Q2, all over. Now let's consider the distance. So from here to there, the distance is 0.16 squared. Okay, we'll subtract that from K, and then Q1, and then it's going to be Q3, all over. Now the distance from here to here is 16, which makes 0.32, and that'll be squared. All right, so then we could figure out that force. I'll save us some time because I know you guys can plug that in your calculator. When you calculate that one, you should get an answer of 63 newtons, and it's going to be, we get a positive 63, so that is telling us that the direction is, this one's going to be a little bit bigger, so it'd be going that way. If we would have calculated a negative 63, well then that means that this force would be greater, so it'd be going that way. I will leave 27 for you guys. So yeah, this isn't anything new. We know how to combine vectors, so you guys will have fun with this section. And you guys know that vectors can cancel out. You guys know how to graph vectors. It's always head to tail. And then the sum of them can be found using Newton's second law. So here's kind of a fun conceptual problem for us to consider. Let's say we have a negative charge Q, and it's to be placed at either point A or point B in the accompanying figure. Assume that points A and B lie on a line that is midway between the two positive charges. Is the total force on negative Q at point A greater than, less than, or equal to the total force on negative Q at point B? So here's what we're saying. Let's say we have a negative Q charge, and we put it at point B and at point A. Okay? Where is it going to be? Is it going to be greater, the same, equal? So what's happening there? Well, if you draw in your free body diagram, you can start to answer this question. Well, at point A, let's just say you put a negative Q here. Well, you have forces acting on it. Well, one is going to be attracted here. One's going to be attracted here, but they cancel out. So really, if you were to put the negative Q here, nothing's happening. Or you're getting a net force equal to 0. Now, if your negative Q is here, and actually I can draw this in on the diagram, you have two forces, right? You have this force from here, and you have this force from here. So then when you take this force arrow and put it down here, head to tail, right? Take and put that one there. You're going to get a net force acting downwards. So like it says right here, the total force at point A is less than the total force at point B. So if you put it right here, it's going to be, the force is 0. Put it here, there'll be a lot more force. So that's just kind of a fun concept to consider. Let's see here. I'm going to skip this on the sphere. You guys can certainly feel free to read up on it, but I'm not going to test you guys on the sphere. So yeah, that'll be a wrap on combining electric forces. Like I said, it's not anything new. You guys know how to do this. So just doing a quick summary. It's not anything new. You guys know how to combine electric forces. So, all right.